Good morning, everyone. I would like to introduce Professor Manoj Gupta, Associate Professor, NSU, Singapore. He has a PhD degree from University of California at Iran, USA. He has more than 550 international journals and more than 200 conference publications. His research areas include microwave processing and disintegrated melt deposition processing, magnesium-based biomaterials, including composite materials, lightweight materials with current focus on nanocomposites, synthetic composites, and metastable composites. He has international collaborations with universities in India, Qatar, UAE, USA, Hong Kong, China, France, Oman, Iran, Egypt, and Sweden. Thank you, sir, for being here with us. Now, I would like to hand over the session to you.
Okay, so I'm going to share my screen now here. Hello everyone, I would like to say good morning from the India point of time, and here in Singapore we are about 2.5 hours ahead, so it's a afternoon time for us. Welcome everyone. The main purpose of my talk is to introduce all of you to a wonderful material, magnesium, and how it is emerging in engineering and biomedical applications. Now, if you look at the bottom of the slide, for example, you see that this metal is not new to engineers, and this widespread use was realized way back during the Second World War. And you can see the picture on your left hand side. In 1943, you see a lot of ladies out there who are working to use magnesium for the tracer bullets, for the bombs, and for the lightweight equipment. So they understood at that time that lightweighting is very important for a very simple reason, that there was a scarcity of fossil fuel during the Second World War time. So they wanted to make everything very light. In 1947, the year when we got our independence, you see the use of magnesium was already there in the commercial aerospace sector. And you can see that there's a Convair XC-99 aircraft which use almost 200 kg of magnesium. And if you have seen this Hollywood movies, Herbie Goes Banana and all this thing, they use this Beetle car, and that Beetle car way back in 1950 used almost 20 kg of magnesium. So what is required for choosing a material in 21st century? I will emphasize 21st century. For a suitable material, you need that this material has to be abundant, because if it is abundant, it will be sustainable. The second thing is that this material has to be non-toxic, because you cannot afford to use toxic material for the sake of our own generation and the future generation. Billions of dollars are spent now these days to clean the water bodies and the land bodies for a very simple reason, that we were not careful in the last century to use the materials which were not toxic. Besides these two factors, the material that is there has to exhibit acceptable properties. If the properties are not acceptable, we cannot use in the application. And finally, it should be cost friendly. That means a material can be wonderful, but if it is very expensive, you cannot take it to a common application for a common man. So these are the four factors which are absolutely necessary in 21st century to choose a suitable material. And for that purpose, magnesium fits the bill very well. Going further, why magnesium? For the four reasons: that it can make the planet Earth a better living place, it can make your plants healthier, it can make humans healthier, and it can also make the animals healthier. So let's go one by one here. What makes our planet Earth a happy Earth? The main problem that we are facing these days is the global warming. You have seen in India, for example, in the city of Chennai, that in December 2015, we had flash floods because a month of rain fell in about 7 days' time. the drainage system could not take care of it, and we had flash floods, and billions of dollars were lost in terms of all the low-lying industry, including IIT Chennai, where half of the campus was flooded and many equipment were destroyed because of these flash floods. Now, if you look in January 2016, we have seen the fire in Alberta when the temperature was about minus 10 degrees centigrade. What made this fire in minus 10 degrees centigrade? It was because of air was just too dry, and that led to the fire of the forests, and a lot of money was lost in there. Now, if you look at, someone raise a hand, I think everything is okay. Yeah, all right. Now, if you look at the Chennai itself in 2019, we had the drought. And if you look at in Europe, for example, the France sizzling at 45 degrees centigrade in 2019. So these are the unusual weather patterns which we have never seen before. Now, if you look at this image, you will see an iceberg coming up from Arctic Circle, and this kind of sites are becoming more and more common. It visited a town in Canada, and that indicates that Arctic ice is melting, and that's a consequence of global warming. In a very recent news, you will see that the ice in the Arctic Circle is turning green. Now, this green, the latest theory, which has just come about a week back, is because the growth of phytoplankton. That means the ice sheet is thinning and the sunlight can go down, and now the plants are blooming now. So this shows that there are a lot of climate change coming as a consequence of global warming. So as a result of this global changes, the scientists were trying to come together in the early part of this century, and they ratified the Paris Agreement finally in 2016. The main outline of the Paris Agreement was that we had to keep the global temperature 2 degrees C below the pre-industrial level, which is at 1880, and we should actually ideally keep it below 1.5 degrees centigrade. The reason is that they say that if we exceed 1.5 degrees centigrade, the frequency of these severe storms, cyclones, droughts will increase very significantly. And if we go beyond 2 degrees centigrade, then all these changes will be irreversible. That means we cannot afford to change the climate back to its pre-industrial time. And currently we are at about 1.2 degrees centigrade about the pre-industrial time. So we have only 0.3 degrees centigrade to play with. To realize this, we have to cut the CO2 emissions by about 2 billion tons by 2025. And that was a target set at this point of time. Now, very interestingly, the COVID came in, and COVID has a lot of issues on its own, but in one respect, it has helped the global warming because you know that you cannot go outside, you cannot travel, you can't drive your car easily, you can't take a plane, the ground transportation has stopped, the marine transportation has stopped, the land transportation in terms of trains have almost stopped, and that has led to the 17% reduction in the greenhouse gas emissions. And they are predicting that we will be able to cut down 2.25 billion tons as per this estimate, and maybe up to 2.5 billion by the end of the year. So in a way, in only one respect, COVID-19 has been a boon for climate change actually. So most of these issues actually come from burning of fossil fuel, because that's the main source of the greenhouse gas emissions. And among the different sector, if you look at this chart here, you will see the transportation sector has a very significant contribution to the CO2 emission. Now, transportation sector, all these numbers keeps changing. They're very dynamic and they will significantly change in this year, but irrespective, industrial sector, electricity sector, and the transportation sector are the main users or consumers of fossil fuels, and we have to reduce it. So in the transportation sector, for example, If you make the vehicle light, whether it's your plane or it's a car or it's your cycle or it's a train, you will consume less fuel. And once you reduce the vehicle mass, you can go extra miles. So that means your mileage will increase and the CO2 emission will reduce. Now, if you look at the European Commission, for example, here, they also try to take steps to reduce the CO2 emission. And what you can see here is they targeted about 20 to 25% reduction in the fossil fuel consumption in the transportation sector. And they took this initiative in 2010, and they wanted to reduce the carbon emission from 130 gram of CO2 per kilometer to about 95 gram of CO2 by 2020. We do not have the figures now, but I'm hopeful that they have made some reductions. That translates to about a mileage of 30 kilometers per liter. So, knowing all this global warming, let's try to have a snapshot of the health of planet Earth, and you'll be surprised that we are in the mass extinction event. That's the sixth in last half billion years. The CO2 levels in the atmosphere are very high, and you are seeing the consequences of global warming. Arctic Ocean, if the thing goes on like this, beside this COVID-19 break, it can be free from ice by 2030. And all this ice will melt. The sea levels will rise by up to 3.4 millimeter per year. And it has already been risen from 1993 to about 2 years back to about 84.8 mm. That means a very bad news for low-lying countries like Bangladesh, like Maldives, like Fiji, and many other countries. And obviously the extreme events, which have already doubled, may further double if we don't stop this CO2 emission. So keeping this in mind, hopefully you are aware of the doomsday clock. In 2018, this doomsday clock was moved to 2 minutes to 12. That means once it has 12, that means we are going to see or witness tremendous catastrophe. And the movement of this doomsday clock is a function of proliferation of nuclear weapons, climate change, and the new technologies. Of course, we have a reasonable control on the nuclear weapons, but the climate change is a very big factor, and the technology we develop as a researcher is also very important. We should not be developing the technologies that are toxic to the land bodies and the water bodies and to the air. So let's bring the mythology now in our scientific pursuit. And you see that in about 3114 before Common Era, Mayan people predicted the end of the world on 21st of December 2012. And as per the Hindu philosophy, we predicted the end of Kali Yuga in 2025 of Common Era. So 2012 and 2025 are practically the window I think the God has given to us to correct our act in terms of science and technology. Otherwise, the catastrophe will befall on us. It doesn't mean that everyone will cease to live, but yes, we'll see very tough time. Many people across the world, especially the younger generation, has identified that where we are heading. And you can see there are a lot of protests coming up every year in many, many advanced countries where they're protesting to go for keep the earth clean. That is very important. Keep the earth green. That's also very important. And of course, some of the placards which are not in English, but apparently they're all protesting against the climate change. So that is the planet Earth. Let's go to the plants. How magnesium is relevant to healthy plants. The work done in Australia, for example, has shown that whatever goes in the soil may end up in the plant. The figure on the top, you will see that eucalyptus leaf showing traces of gold. And in the two pictures below, you will see that the plants are able to absorb manganese and other elements which are present in the soil. So basically, what this research says is that if your soil is contaminated, then you will end up with those elements on your dinner plate. No matter how much you wash your vegetable, the contamination is already there. What is the most lightweight element that we are using these days? And it is aluminum. And aluminum is a toxic element. Maybe many of you do not know about it. Now, if the aluminum is not properly recycled, it may end up in our food chain. But for aluminum to be absorbed by the plants, the pH of the soil has to be less than 5.5. And you'll be surprised that 60% of the world crop growing land is highly acidic. So that means if we use aluminum, we have to be extremely responsible. Now, what happens if the magnesium enters our food chain? You will see the plant on your right hand side with the longer roots and everything. That's the one which is exposed to if your soil is magnesium sufficient rather than the soil which is magnesium deficient. So basically it's a nutritional element for the plants. So you can get much more crop growth if you have magnesium as one of the ingredients which goes in the fertilizers, for example. Now let's try to see the relevance of magnesium for the humans and animals. If you're not careful with our technology, for example, the picture on your left-hand side, you'll see a dog turning blue because it was drinking contaminated water from a river in Mumbai. And the picture on the right-hand side, you'll see Hulk from famous movie series, Avengers, and you see that his body is contaminated by some other means. So what this two example tells you is that we cannot pursue with the toxic technologies. These things which is a fiction can become a reality if we do not take the timely step. So how does magnesium relate to the human health? It is involved in the 300 chemical reaction. It is required by muscles, nerves, heart, immune system, muscle tension. If you're feeling low energy or trouble sleeping, you can use magnesium supplement. Up from 250 mg to about 400 milligram you can take every day. It's a nutritional element for humans as well as animals. To note that magnesium ion is the fourth most abundant cation in the human body, and it is stored in bones, also help in fighting osteoporosity. Now have a look at aluminium. To note that approximately 3.8 million tons generated in 2017 and 2.7 million tons, almost 75% of them are landfilled and they can enter the food chain. Now, if aluminum do come in the food chain, it can lead to the cognitive deficiency, dementia, adverse effect on central nervous system, and the reproductive system. Its link with the Alzheimer's disease is very well established. And the people who are very susceptible are the same as the people who are susceptible to the COVID-19, infants, elderly people, patients with the impaired renal function. So as a result of that, people are trying to, or WHO for that example is trying to advise the people to reduce the aluminum intake, and they keep changing these numbers from time to time. Magnesium is also can be used as a medicine. For example, in USA, 15% of the people suffer from tinnitus. And apparently, if you take magnesium supplement with vitamins A, C, and E, you can find this tinnitus situation. And many of us are exposed to the noisy situation, especially the soldiers, workers, and the normal individual working in the machine workshops, and so on and so forth. So the people from last 20-25 years have been very active in also taking magnesium because it's a nutritional element. Body loves magnesium. Body needs magnesium. After the calcium, it is the most required element in the human body. So people in Germany are very active in developing biomaterials, and they have already put magnesium stent in the body and the compression screws in the body. Once you use these magnesium screws, you don't have to take them out, and that reduces a lot of medical costs and the patient trauma, as you will see later. Now let's move on to the electromagnetic shielding. Every electronic component that or equipment that you use in your daily life emit electromagnetic radiation. Now, you'll be surprised that electromagnetic radiation is the fifth largest pollution after noise, water, air, and solid waste pollution. It does not see any boundary. Every human being is susceptible. So what really happened? When you use this equipment or when you use it next to you, like TVs, like refrigerator, like food grinder, and so on and so forth, The magnetic component of the electromagnetic radiation create current in your body. Your body doesn't know how to handle this current. And when the body doesn't know how to handle the current, it leads to adverse effects on the metabolism and hormone production. And as a result of this, WHO has classified electromagnetic radiation as possibly carcinogenic. Note that this damage accumulates over the time. If you are exposed, that dose stays in your body. And once it exceeds certain level, then you start seeing the side effect. So basically, when you are young and energetic and your body is very strong, you may not see the effect. When you grow old, then you will start seeing the effect. So possibly when you're sleeping in the night, stay away from any electronic gadget that you have because you are increasing your dose. So we try to investigate magnesium as a material to absorb the electromagnetic radiation. Aluminum is used currently, and you can see that in the radio wave frequency, magnesium is superior, and in the microwave frequency, magnesium is similar in performance as that of aluminum with a similar mechanical properties like hardness. So why should I replace aluminum with magnesium? One simple reason: aluminum is toxic, magnesium is not toxic. You can afford to throw magnesium anywhere, and it is not going to toxify the land body and the air body, and it will also make your laptop and your phone a lighter gadget, so it's easy for you to carry. So it's the time to use magnesium. Let's try to understand the positive aspects of magnesium, which comes in the group 2A of the periodic table of elements. Melting points, very low, 650 degrees C. Its density, one of the lightest metallic material that can be used in the structural application. Wonderful specific strength, wonderful damping, and wonderful electromagnetic shielding. Acceptable properties: ductility, more than 5%, so it can be shaped. Modulus, 40 to 45 GPa, make it wonderful as a biomaterial, but at the same time cannot be used in the stiffness-based designs. Its cost is reasonable, slightly more expensive than aluminum. Negatives: it corrodes very fast, so we need to have the coating technology if you are using magnesium in application. Similar to what we do to steels, you know that all the steels are coated with paint or galvanized, so we have to find very good techniques for magnesium as well. Let's try to compare magnesium with the workhorses of engineering and biomedical application: aluminum, titanium, and steels. Now, if you look at the density, you see that it has a lowest density, as I have indicated before. It has a lowest melting point among all these materials. Its specific modulus is similar to all these materials, and its specific strength is only next to titanium. And with the fact that it may be about 5 to 8 times cheaper than titanium, so it makes it a cost-effective material. It can be processed using low energy. It has excellent castability. That means it can be shaped better and it can be machined better. So that means this is what we need for the industry. It can be turned into finished product faster, saving a lot of man hours. So are we short of magnesium? Remember one of the slide, it should be abundant. So are we short of magnesium? Not really. It's the sixth most abundant element in the earth crust, 2% by mass, and it's the third most dissolved mineral in the seawater. Okay, how much is magnesium? It is 12 times more than aluminum. So that means if we can use aluminum resources for 100 years, you can use the magnesium resources for 1200 years. And if you look in the universe now, you see that, and you'll be surprised that magnesium is the most widely found element in the whole universe, even more than iron. So that's what I always say, magnesium is the God's own element, is the God's favorite element. So if you're trying to colonize Mars, the picture you can see here, or you want to colonize Moon, you will always get magnesium there. So now, what happened between 1950 and 2000? Why people stopped using magnesium? And that is the famous picture from Finding Nemo movie, which was a super hit. And this Merlin, which represents the research community, is asking, so why you gave up the magnesium? And the Dory, who used to have the short-term memory loss, it says that 50 years of memory loss. Anyway, people woke up, the researcher woke up, the community woke up, and they started investing in magnesium technology. The notable countries which really started very early are China, then South Korea, Germany, Japan. Russia is always there. So to understand more, to give you more idea about the potential of magnesium where India is greatly lacking, is first is the automotive sector. As I indicated this example, Beetle car used 20 kg of magnesium. It was also used way back in 1970 in the engine component. People say magnesium is flammable, but they are misinformed. It will not catch fire below 580 degrees centigrade. And even the aircraft skin, the fighter aircraft skin at the max speed reaches only 100, 120 degrees centigrade. So magnesium can easily be used in most of the application. General Motor introduced magnesium in the boot area of the car in 2012 simply by saying 75% lighter than steel, 35 about 33% lighter than aluminum. They want to cut down the fuel consumption, so they launched it. Brand name like Porsche, they started using magnesium in the rooftop of the car. They compared magnesium with the aluminum, and they also compared magnesium with the CFRP, carbon fiber reinforced plastic, and they found that magnesium was the thinnest, strongest, and lightest. And they, just by replacing the roof, they were able to save 10 kg of the weight from the car. So that's another example. South Korea has been very aggressive from 2004, and they have used magnesium in, for example, the wheels, in the steering wheel. Even the Suzuki, Maruti Suzuki is also using magnesium steering wheel, lamp casing, and so many places. So the magnesium demand logically is increasing. But many of the company will not share the data with you because everyone want to maintain their key selling point, which is a lightweight and which is a less fuel consumption. So the US people wanted to increase the amount of magnesium in the car from 5 kg way back in about 2010 to about 160 kg by 2020. I do not have the new numbers, how much it is, but that is about 3,200% increase. And that shows how big is going to be the market of magnesium in the automotive sector. Now you ask yourself, do we have anything like that in India? The answer is no. Now let's move on to the potential in the aerospace sector. Now, way back in 1947, this picture on your left-hand side, I showed it, that is a Convair aircraft used very high amount of magnesium there because that time was the time when the fuel was scarce. Between 1949 to 1959, you have Convair B-36 Peacemaker, and they use 8.6 tons of magnesium. Sikorsky helicopter used 115 kg of magnesium. Lockheed F-80C Shooting Star, completely made of magnesium. Russian bomber, 1.5 tons of magnesium. So based on all this information and keeping the climate change in the mind, FAA, Federal Aviation Authority, have finally said that, okay, we can use magnesium in the commercial planes. It was always used in defense sector, but not in the commercial sector. Now, its implication you can see in the last line highlighted in yellow or with the yellow font. You save 360 kg in a narrow A318 bus, while 4.2 tons in a A380 wide plane. And 4.2 tons means how much cargo it can carry now and how much less fuel it will use can be visualized by any one of you. Maritime. Let's look at the maritime. Amphibious vehicles are the defense vehicles which can operate in the land as well as in the water. They also need to move faster. They also need to save on the fuel. In the wartime, you have more fuel, you can last in the battlefield for a longer time. And they are using magnesium. The cruise ships, most of the engines are made of magnesiums. And in the defense application, armed robotic vehicles, for example, if you use magnesium in there, make it lighter, they can stay in the war zone longer time. How much you save? 1 ton for a 6-ton armed robotic vehicle. And if it's a big one, you can save up to 3.75 tons for a 25 tons, which is almost like 15 to 17% of the weight saving, which is very tremendous. So these are only some of the applications for you to appreciate, and I have not yet talked about the structural component in electronic sector. For example, Samsung is using magnesium for the casing of the phones that you use. Robotics, people are looking for it. High-speed trains, Japanese are already working and are in the advanced stage. There are many, many other sectors which are emerging from that. So it has very, very big scope industry, especially in a country like India. We have almost no infrastructure. So now, what are the techniques that we have developed to make this material? Now you will see that what properties and what kind of properties you can get from these kind of material, because there's another factor for the use of material. So any metallic material can be made using a casting route. We call it liquid metallurgy route or the powder metallurgy route, where we use the powder to start with. We tried many magnesium and magnesium based alloys and many different type of reinforcement over the last 20 years. And this slide shows you the disintegrated melt deposition technique that we developed in our lab way back in 1995. What we do is that we take a graphite crucible, we put the material in the crucible, we use a resistance heating furnace, very cheap, and take it to 750 degrees centigrade. We stir the material with the reinforcement, we bottom pour it, and when the metal is pouring, you hit with argon gas jets to disintegrate that, and then you deposit that into an ingot. And a typical facilities which we got for about $25,000 is shown here in the lab. You can get an ingot the way the industry want to have it. You can mush it into billet. You can also extrude it. For the powder metallurgy route, normally people mix the magnesium powder with the reinforcement. They blend it. They use either V-blender or the planetary ball mill. They compact it, and then you can sinter it. Sintering, people use the tube furnaces. It takes about 2 hours for a 1.5 inch thick sample, but we try to move on to the microwave because it's an energy saver. So what we did was that we use a microwave exactly the same that you use in your household. We created a setup of the for the insulation here. Here's a crucible, inside crucible. Here's an outside crucible. Between that, we put the silicon carbide particle. We put the billet in here that need to be sintered. We pre-calibrated the microwave. We switch it on, say for 14 minutes, it reaches a temperature of 640 degrees centigrade, and we switch it off. That's all we have to do, switch on, switch off. So we are able to sinter in 14 minutes when the conventional technique takes 170 minutes. That is a saving of 91% in the heating duration. Why it is important? Now you are able to almost sinter 10 parts rather than 1 part in the same time. Temperature 640. We can increase the rate of sintering. Remember the Arrhenius law, any reaction is an exponential function of temperature. We can even do the sintering in air and no need to use in the argon. How much energy we save, and you can translate that into the fuel consumption, 90 to 96% in this situation. So basically it's a very energy saver. So this is how it works. Switch on the microwave, microwave heats the susceptor, it heats the billet from outside to inside, and the microwave heat the billet from inside to outside. So there are 2 heating fronts, inside to outside, outside to inside. And that is very effective in giving a homogeneous temperature distribution and the homogeneous microstructure of the billet. Efforts are being made to take this to the industrial level now. You can get the billet, you can extrude that, no defects, nothing. And the cost of this setup is only like $2,000. Very cheap. So once you have made a material, you claim your material is good, you claim your processing is good, but it is no good unless it also shows good properties. So you have to characterize your material from a microstructure perspective, from mechanical perspective, and also from the corrosion perspective. So we focus on nanocomposites. In the nanocomposite, you disperse the nano-sized reinforcement like the one you see on the right-hand side, Al2O3 particles there. And on the left-hand side, you see the micron-sized particle. What is the difference? The size of the particle. we try to go for the nano size particle, and we call that as a nano composite. Now, why it is important to put the nano size particle? If you use the micron size particle, for example, they either tend to crack, as you can see on the left-hand side image, or they tend to debond, as you can see in the right-hand side image. Both of this particle damage mechanism lead to the compromise in the mechanical properties. They are the site of crack nucleation, which will eventually grow and fail your material. Nanoparticle don't do that, and that is why we go for the nanocomposite technology. With respect to the magnesium, which is a hexagonal close-packed material, you can improve the ductility of magnesium by putting nanoparticles. You can improve the modulus, you can improve the dynamic properties, high temperature stability, creep properties, wear properties, fatigue properties, dry and wet corrosion properties, ignition characteristics, electromagnetic interference, and the bioresponse. So just by putting nanoparticles in the small amount, you can achieve all these different properties. So we started with microwave. We put very fine, small amount of nano size aluminum particle. And look at this highlighted red font row here, which only shows you a point that by putting the nanoparticles in a very small amount, 0.5 volume percent, you can get a simultaneous improvement of the yield strength from 134 to 218 megapascal, ultimate tensile strength from 190 to 271 megapascal, and you can make the ductility 1.5 times from 4.6 to about 6.2. And this is amazing because now you're improving both strength and ductility of a material just by putting 0.5% of aluminum. And this is possible to disperse the metal particles, which are soluble, only because we use the microwave processing technique. We also use the ceramics. I'll give you only one example. We have tested almost hundreds type of ceramics. Now, if you put boron carbide by 1%, for example, you see the yield strength is going up, UTS is going up, and the ductility becomes 3 times. If you want more improvement in the strength, put more, 1.74%. Again, you have an increase in the strength. Ductility now, instead of 3 times, it is 2 times, but still quite high. And with this kind of ductility, your material is very tough and it can be easily shaped. Now look at the compressive properties, same trend. You are increasing the yield strength, compressive ultimate strength, and your ductility is not compromised. It is still marginally up. So basically your material is becoming much more tougher than the base material. And that is the magic of nanoparticles. We are also involved in developing new alloys. For example, we developed this alloy, magnesium 4 zinc, 3 gadolinium, and 1 calcium. And you see some of the properties here, 260 megapascal, UCS is 585, failure strain is 12.6. Anything about 10 is wonderful, and your grain size is very low. So what is the importance of this number? These numbers tells you that these properties of this simple alloy is better than WE43, WE44, and ME21. Now these are the aerospace alloys, which are very expensive. So you don't have to buy these alloys. You can make your own alloys, which are better than that. And then you see the magic of nano reinforcement. You put zinc oxide in there, about 1.5%, I think, and the strength goes up to 355. UCS goes up to 703 megapascal. Failure strain stays about 10%. Grain size goes down. Now, what is the importance of these numbers here? The importance here is that these numbers exceed not only these aerospace alloys, but also the mild steels. So that means magnesium-based materials can not only replace aluminum-based material, but they can also replace steels where you can get the 75% weight saving. And that is where magnesium is going to come in very, very strongly. Tensile and compressive uniaxial properties are important, but so are the cyclic behavior of the material. And that is a work we did in collaboration with the University of Akron with Professor T.S. Srivatsan. And you see that in this case, we use a commercial AZ31 magnesium alloy, and we put CNT, carbon nanotube. And now you see, as expected, the yield strength goes up, 203 to 237. UTS goes up, 294 to 302. ductility goes up 13.2 to 16.8. So pure magnesium results are reflected by the commercial alloys. And if you look at this graph, SN graph, stress versus number of cycles to failure, you see the curve of composite is always at the higher side. That means for a given stress, it will show a much more number of cycles to failure. If you don't have CNT, if it is expensive, you can also use AL203, very cheaply available, internationally available particle, nano size, 50 nanometer. You even use it for polishing your samples. And once again, it shows a better behavior, SN behavior. For a given stress, much more number of cycles to failure. Dynamic behavior, some of the behavior which is used by the transportation company like the car manufacturers. In the case of collisions or accident, you are exposed to the loading at a high rate, high strain rate. That means your load is applied in a very short period of time. So I did some work with my colleague who was expert in using split Hopkinson bar, and I will show you this graph. Only see the blue curve here, which is a stress strain response in the dynamic loading for the pure magnesium, and not pure magnesium, AZ31, and the black curve, which is a nano composite using Al2O3 particles. And you see that under the dynamic loading, the nano composite shows higher strength levels and also the higher ductility level. So it's again a good news for the auto sector. High temperature behavior, part of the work done in collaboration with ISM Dhanbad. Professor Ashish Malik is sitting there. And apparently what you see here is at all the temperature, which you see on the on the x-axis here in the graph, you see that the composite with the blue squares is always remains superior to that of monolithic material. So that means these materials will have a higher durability when compared to the monolithic material. To take it further, we also did some creep work in collaboration with researchers in Germany, Professor Hort and Hajo, and we gave them a new alloy in which we replaced aluminum by tin. Our results were positive, hardness goes up, compressive yield strength goes up, and the UCS goes up, ductility marginally goes up. Then we put zinc oxide particles, 1.5%. Again, we see an increase. Again, we see an increase in the strength levels. And the ductility is 27.4, much higher than aluminum alloys that you can think of. So that's a magic again of the nanoparticles. So we gave them this material and they did the creep studies, and you see the blue curve correspond to the nano composite and is always better than that of the monolithic material. So that means the creep response of the nano composite is superior than that of the monolithic material. Sliding is another engineering application that is commonly seen in many applications, automotive industry, tracks, railways, and everything. So putting the nanoparticles like Al2O3 also help AZ31 to improve their tribological performance or the wear performance by up to 25%, and that is with only 1.5 volume percentage of Al2O3. If you want to increase more, you put more calcium, 1 to 3%, you get another 25% increase. And what you are getting now is almost like 50% increase. So 1.5 times the life cycle. Machining is also very important facet if you want to take the material to the industry, because most of the components are machined. And this work we did, the initial work was done with IIT Delhi, Professor Arivandan, and they wanted to study the machining aspect for the deep aspect ratio holes, and their results showed that we can drill it, no abnormal arcing, and the surface roughness is acceptable. Some of the pictures that they shared to verify their observation. We also did some machining work with the Newcastle University, both in Singapore and UK. We gave them a number of nanocomposite based on magnesium, and they say the cutting force for all the nanocomposite is lower except for only one material, and they are able to get a good surface roughness as well. So you can make the machining faster. Now, how about when you put a material into the application? It should not corrode. So how does this nanoparticle affect the dry corrosion or the oxidation behavior. So we did work on a number of temperature. If you look at this graph, the AZ31 commercial magnesium alloys shows the more weight change when compared to the AZ31 with 1.5% Al2O3 particle. This can be attributed to the defined microstructure of the material. So if you look at the picture on your left hand side, you see there's an oxide layer which is a bit thicker, and on the right hand side, which is of the composite, is more compact and thinner. Now, in a similar work done in Australia, but of course not on magnesium but on steel, they showed that if you refine the microstructure, the diffusion of the ions from the bulk to the surface increases, and that increases the corrosion resistance of a material. And similar observation we have found there. Our microstructure was refined, layer was thinner, compactor, and if you scratch it, the ions will come in and repair the layer. So that is in confirmation or conformance with the work done elsewhere on other materials. We also did the salt water corrosion response of the nanocomposite in collaboration with late Professor Balasubramaniam from IIT Kanpur. And we sent the samples to them, and he found that if you put, for example, 1.5% Al2O3 in commercial alloy AZ31, you almost reduce the corrosion rate to 1/3, and he attributed that to the reduction of the cathodic phases in the microstructure. So if you reduce the number of cathodic phases in the microstructure, the rate of corrosion goes down. So we did a lot of work, and part of the work is kind of summarized in this slide. So we use metallic reinforcement, we use hybrid reinforcement, we use the ceramic reinforcement. And so here's the bubble chart, which also differentiate between, we have used this liquid casting method in this gray area, and this bright orange area is the powder metallurgy zone. And depending on the strength and the ductility that you want for your application or the requirement of your application, you can choose a material from this kind of charts. You can choose a type of processing from this kind of charts and simply take it to the industry. Ignition, very big misconception in the scientific and the normal community that magnesium can catch fire. But to note that magnesium can ignite when it is taken to a temperature of 581 degrees centigrade. If you put nano reinforcement, you can simply improve the ignition temperature to 611. And this graph on the top side says that amount of reinforcement lead to increase in the ignition temperature. It also reduces the thermal conductivity of the material, and also the ignition temperature is increased. So we should not worry about it, because all the electronic gadgets, including the aerospace, defense sector, and normal automobile sector, you use electronic gadgets, electronic control, and the solder that go in that electronic system melts at about 232 degrees centigrade. So if someone has to really sabotage your system, your electronic system is the first one to go. And to reach 580 degrees centigrade is not very easy and humanly possible unless there's a very deliberate amount. Let's try to look at the magnesium as a biomaterial. I'm trying to see whether this clip works, which we have just simply launched a company, and see if you can have a look at this clip.
Sir, it is not visible there on our screen. But this video is not visible to our screens.
So if you see that, that's a very, hello?
Excuse me, sir.
Yeah.
The video is not visible to our screen, sir.
Oh, okay. Means at least they're able to hear it, right? Which
No,
is,
sir. Not actually.
so they're not able to hear also.
Yes, sir.
Anyway, I think it is optional, so it's okay. I can just continue on.
Okay.
Yeah. All right. So I realized that you people have missed the video. It was working on my screen, but for various reasons, it was not shared. I thought it should have been shared because it was a part of the PPT. But anyway, the message is like this one. Uh, as you've seen that magnesium is a nutritional element and we need the implant. It's a very, very big market. It's almost $2 billion market nowadays. And we need the implants. Suppose we have a fracture or a hairline crack or something. What people do? What doctor do? They put a steel nail, they put it, the thing is healed, they take it out. So you go for one surgery to put an implant inside and one more surgery to take it outside. So you have two surgeries, double the cost. If you put magnesium screws or plates to fix the fracture, you put it in and you forget about it because it is going to get dissolved over the time. So you save on the second surgery. That means your 50% of the hospital cost is reduced. And that is the driving force of using magnesium. And that was a message which was in the video. So we tried to use the nanocomposites and we saw that, or we tried titanium diboride, oxide, carbide, and nitride. The first thing when you want to use a material to see that whether the properties are superior to that of bone, because we are trying to fix a bone here. So the properties of bone are shown in the green box here, 149 megapascal with a ductility of not more than 2.1%. And you see that all the properties you see in the table exceed that. So first we verified tensile properties, then we verified the compressive properties, which was also much more exceeding. So that means magnesium is a stronger element because it has both higher strength and ductility when compared to the bone. Then we have to try these materials into a physiological medium, DMEM. It's a standard available medium in the market. And you follow a certain ASTM standard, in this case G3172, and you find the corrosion rate. The corrosion rate was 0.1 mm per year. So what does the surgeon want? So what is this number actually? The surgeon wants about 0.2 mm per year and lower. And that gives enough time for your injury to heal. So they are able to show that corrosion rates. That means they will not be dissolving much faster. Having said that, it's not like you put any nanoparticle in any amount and you will get the best properties. You have to do experiment. You have to do literature search. You have to see what is the best. One of the outcome of magnesium dissolution in the body is the increase in the pH. You don't want the pH to increase too much. So for example, if you look at this graph on the top left-hand side, you will see that if I put 2.5% of TiO2 for 50 days, my pH increase is only about 7.5 here. So I will choose magnesium 2.5 TiO2. Similarly, for TIC, I will choose magnesium 2% TIC. And for TIN, I will use about 2% TIN. So I will choose one of these materials with a specific composition. And obviously, slight pH increase is okay because it can help in oxygen pickup and it can minimize the bone resorption, but too much pH can lead to the microtoxicity. So we are actually currently working with the doctors here in the hospital for mandibular reconstruction. We gave some of the nanocomposite to them, magnesium with nanohydroxyapatite, and they checked on the cell viability. it has to be more than 75%. So all our material passed based on their test. Then they also did one more test, which is called as the LDH test, and it has to show zero or mild toxicity. So all our material, including pure magnesium, of course, are less than 25%. Only the one with 1.5 cerium oxide is 27.5%, but it is acceptable because it's only in the mild zone. We also tried hollow silicon nanosphere, and obviously it improved the properties as we have seen many times before, and it can also give us a very low corrosion rate. So once again, remember, silica is called as bioglass. It can be used in the human body. So where we are heading to now, we are trying to improve all these facets to make magnesium a better material in both body and in the engineering application. We are also trying to develop very lightweight, I will say ultra lightweight magnesium based material, which can float in water. So you throw it in the water, it will float there. And you can see this, for example, by putting lithium in there, this piece is floating. And while the pure magnesium is settling on the surface. So we have reached to this level and we are further improving onto that. So in conclusion, I would like to say that there's a tremendous scope of magnesium, magnesium alloys, magnesium composites. I've already highlighted nano composite, but then there are metastable composite. There are syntactic composites also, and they are all equally considered for engineering and biomedical application. Multi-billion-dollar market for grab. Of course, you need the industry to support you, and they should have the vision. Now, you can use other thing which industry looks is that, do I have to put a lot of money to manufacture this material? The answer is no. You can use the conventional processing method that already exists to melt aluminum, for example, and you can easily replace with magnesium with minimal tweaks. So there's no additional infrastructure cost per se. Then if you use nanoparticle, for example, you can also help in improving many properties together, and that are exactly very important for engineering and biomedical application of this material. And as I say, there are other reinforcement, amorphous reinforcement, which lead to the metastable composite, and hollow reinforcement, which lead to the syntactic composite, are also being pursued. Because if you want to make ultra light material, if you want to really replace plastics, which everyone knows is a nuisance, and in many cities in India it is totally banned, and it has already entered the human food chain, and we do not know how it's going to react with our health in the years to come. So you have to make it ultra light, and that is where more efforts are going on. So in a nutshell, magnesium technology has arrived and is a time for industry to adapt for their own benefit. Like even in India, it's a 1.2 billion people, and it's a big market. If you just cater to your own market, like South Korea has done it, you can really make a significant difference. And of course, the side benefits are you make a green planet and you improve the health of not yourself, but also your future generation, your children. So with that, I conclude my talk with a slide on acknowledgement to all my postdocs, PhDs, interns, MN students, and bachelor students. Thank you very much. And